Hello, my dear friends. Today I will discuss with you about the Galilean transformations. And Galilean transformation, also known as the Galilean transformation equations, okay? And what they are? Galilean transformation equations connects the measurement of the positions and time coordinates in the two inertial frames of a reference. In relative motion, when one inertial frame, it is in the relative motion with respect to the second one, and with the velocity, keep in mind velocity should not be too large. It should be very small. It should be small as compared to the velocity of light when you discuss the Galilean transformation equations. So there should be two or more frames in relative motion, but main important thing is the relative velocity should be this small. This is a frame S, x-axis, y-axis, z-axis. Now another frame shown with the help of the red lines, and this frame is displaced by some distance because this frame is actually moving, so that's why it is displaced. The origins, they are not coinciding now because we have shown the two frame at time t, which is greater than 0. This frame is an x-axis, y-axis, z-axis, x dash, y dash, z dash, and origin O and O dash, and this is moving with velocity v, and this is equals to this distance is how much in time t. We're thinking like both the frames, they were coinciding at time t equals to 0, and this is the position which is shown here of the two frames. It is after time t. Now the problem is we have to think how much distance traveled by this red frame, mean S dash frame, in time t. Okay. So velocity is equals to, tell me, distance over time, and you can find distance from here, distance moved by the frame S dash. It is equals to how much in time t? Vt. Okay. So this distance is Vt. O to O dash, this distance is Vt. So measurement of the time is started, when it is started, when O and O dash were coinciding. When they were coinciding at t equals to 0. And at time t, S dash is displaced. How much distance? O to O dash. Now you consider an event occur at a point P at here in the frame S. And what is that event? The event may be the collision of the two balls, and even that event can be described by the four coordinates x, y, z and the time t in the frame S. So I'm writing coordinates for the frame S. Okay, these are the coordinates of the point P with respect to S frame. The first three are the Cartesian coordinates, and of the point P. And fourth one, which is the time. It registers the occurrence of the event, right? It registers the occurrence of the event. The event is completely known from the spatial coordinates of the point of its occurrence and then the time coordinates, the time of happening, because we need the time also when that events occur. So event can be the collision between the two particles, or maybe any event. You may think this S dash frame. So in frame S dash, the event can be described by another set of coordinates, similar coordinates, but we'll call as dash, x dash, y dash, z dash, or x prime, y prime, z prime, and t prime. The red mean for the frame S dash, the same coordinates. Okay, so I am marking this line. This is what the point P position vector from the origin O, and this point same event, the space coordinate from the O dash. Okay, then I drawn a perpendicular from this point on the x or x dash axis, right? Now this, how much this distance is already defined, Vt, and this we call it what is the x position with respect to S dash frame from O dash, right? This is x dash. So total is x. What is x? This event P, the distance along x-axis from the S frame. From S frame, distance is how much? X. So this distance is x from the frame S. From S dash, it is distance is x dash. Now the x is equals to, very simple, x is equals to this distance plus this distance. So x is equals to x dash plus Vt. So already I defined O dash A is how much? So x dash is x minus Vt. S dash frame is moving along the x-axis, and there is no relative motion along y and along z, so no change. Y dash remain equals to y, z dash remain equals to z, and you know very well the classical mechanics, what it says, that the time is assumed to be universal in nature. So t dash is equals to t. So we are having a set of equations. So these are called Galilean transformation equations, prime to unprime. And reverse Galilean transformation equations are, so there are two set of equations. One is this is Galilean transformation equations, Galilean transformation equation, and inverse Galilean transformation equations. Okay. So to the observer in the frame S dash, the frame S, if the observer of S dash, the frame S will appear to be moving along in the negative x-axis and with velocity minus v. Actually, Galilean transformations are the equations which connects which connects the measurements of positions and the time in the two inertial frames of reference. In relative motion, like one inertial frame is in motion with respect to the other, in relative motion with respect to each other. With the velocity, and one thing you keep in mind, the velocity here, it is very, very, very much less than the velocity of the light. Very nice. Now one question for you, and try it yourself. You know what that question is? One inertial frame is moving relative to the other in any direction, because I discussed before the frame was moving along x direction. The problem for you is any direction, and you prove this set of Galilean transformation. That's very simple for you, and you can, I think. If you don't, please write me in the comment box. Now, what do we mean by the variant quantities? Variant quantities are those quantities whose values are different for the observer sitting in the different inertial frames. Okay, because the name implies the variant. Example: position, velocity, momentum, etc. Invariant quantities are those quantities value remain the invariant mean no change. The value remain the same and do not depend upon the relative position of the motion of the inertial frames in which the observers are sitting, like mass, length, time, etc. Acceleration force. Now, what is the Einstein's second postulate of relativity? As measured in any inertial frame of reference, light is always propagated in the empty space with a definite velocity c, which is independent of the state of motion of the emitting body, or the speed of light in free space has the same value c in all inertial frame. There is no change in the velocity. Velocity of light cannot be relative. This is Einstein postulate, Now, if we apply the Galilean transformations for a body which is moving very nearly equal to the velocity of light, then by Galilean transformation, in one frame the velocity will be c. But if we observe from the inertial other frame, if one frame is moving with respect to second with velocity v, then the velocity of light will differ in one frame and in the other frame. Already I explained. So c and c dash will be equals to, in one frame c, other frame c dash is equals to c minus v. But this is a contradiction against the Einstein's postulates. So therefore, Galilean transformation breaks if the velocity approaches to the velocity of light. That's a limitation of the Galilean transformation equations. Okay. Now, Galilean transformation equations. Galilean inverse transformation equations, remember, two set. And the equation for velocities, just differentiating this one or this one. Differentiating with respect to time, you can have the velocity transformation equations. And velocity is the variant quantity. Now, if you differentiate the velocity equations with respect to time, then you can have the acceleration equations. And because v is constant, differentiation of v is 0, the acceleration will be invariant. If acceleration invariant, force will be invariant. Okay, the Newton's law will be same in the two inertial frame. Now some question for you. Number 1. You please solve the equation, the questions, and then send it to me. I will check whether your answer are true or false. And very, very important questions for Galilean transformations. Now the question number 3 is force and Newton's law, they in motion are invariant under Galilean transformations. This important question. And last important question is show that the law of conservation of linear momentum and law of conservation of energy are invariant under Galilean transformation. Thank you very much. Please subscribe my channel. This is my request. Okay, thank you. Please you try yourself, please. That's two important questions. Thank you very much.